Hello everyone, my name is Amélie Gruel, and today I will be presenting to you the article Event Data Downscaling for Embedded Computer Vision that my supervisor Jean Martinet and the researchers in Microelectronics Teresa Serrano-Gotarredona² and Bernabé Linares-Barranco and myself have submitted to the VISAPP 2022 conference. To begin this presentation, we'll see what are event cameras. This is a new kind of event-based sensor that has been developed since the 1990s, and it differs from traditional RGB camera by the following mechanisms. Traditional RGB cameras record for each pixel the change in value of the color, red, green, and blue. However, event cameras record the change in luminance. If the luminance gets brighter, then the camera will produce a positive event, and if it gets darker, then it will produce a negative event. These mechanisms produce events that are really asynchronous and that do not wait for frames to be generated in order to happen. And thus, event camera produces really interesting new kind of data that is really sparse but gives all the information about what is moving in a scene or not. Here we have a common example given by Gerrick in this article in 2018. As you can see, in this case, the event camera films a rotating dot on the rotating platform. And here we visualize the events that have been produced according to time. As you can see, there is a really high density of events on the place where there is a dot, a lower density of events where there is a platform that rotates, and all the other events that are generated are just noise. Another example that can be a bit more visual for you is given by the DVS 128 gesture dataset created by IBM, and that records different persons doing different hand movements in front of a camera. Here you have the example of the right hand clockwise with all the positive events presented in green and all the negative events presented in blue. As I said, the events are produced thanks to the luminance that is recorded by the camera. The luminance is translated into log luminance. When the log luminance crosses the threshold going up, a positive event is produced, and if it crosses the threshold going down, a negative event is produced. The whole threshold has to be crossed, as is given here by delta I, and not just one part of the threshold. As you can see, where we reach a maxima, there is no event that is produced when it crosses again the same threshold. In this paper, our goal was to formalize different methods for spatial downscaling of event data. What do we mean by that? We like to modelize how the events produced by the pixel in a X by X region, here in this example a region blue in 2 by 2 pixels, would be represented by the events produced by a similar pixel representing this region in the downscale sensor. Our motivation to do some spatial downscaling for event data are the following. First of all, the event flow of event data can become very high in dynamic and texture scene, such as this one. We can reach up to 25 million events per second, which is a lot to process, even though the event data is already really sparse compared to RGB camera. Furthermore, we are interested in spatial reduction of event data in embedded system, where only relevant information should be stored and processed, and we believe that spatial downscaling is the best way to do that. In many state-of-the-art approaches for event data in embedded system, those problems are solved by putting events into frames, but these mechanisms lead to a huge loss of asynchronicity, which is a main argument for using event data. To our knowledge, only one existing tool exists, which was implemented by Tonic, which is a Python library for neuromorphic data handling, and this class is the transforms.downsample class, which downscales the event data spatially and temporally. Here are the 3 methods that we have formalized in this paper. First of all, there's simple event funneling, then log luminance reconstruction, and finally events to video to events. The simple event funneling is the quickest method that exists. That's the one actually implemented in the Tonic tool. How does it work? We have here an example given by the events produced by 4 fictive pixels that are downscaled into 1 pixel. Here, for simple event funneling, all these events are kept, and the X and Y coordinates are just divided by 4. As I said, the method is really quick and computationally efficient, but this leads to a really saturated image and data. This is easier to understand with an example. Here we have one sample of the DVS 128 gesture dataset that I presented earlier. Here it was, we have, when we divide this sample by 5 using simple event funneling, so already it gets a bit saturated. And when you divide by 10, you can't really understand anything because it's just too many events. This does not lead to a reduction of the event flow as we would like it to have. The second method was a log luminance reconstruction. We believe that by reconstructing the log luminance of the different events produced by the different pixels in order to get the mean of those log luminance, then we will have something really close to what would an actual event camera of downscaled resolution produce. We get those 4 same pixels with those 4 same fictive events that are reduced using an event count. Event count is an approximation. Instead of actually computing the log luminance, we are going to compute the mean threshold reached by the sum of all those events. This threshold corresponds to the mean of events produced, with the positive events adding 1 and the negative events removing 1 to this threshold. So every time we have a new event, then we augment by 0.25, 1 divided by 4. Only when an integer is crossed, then an event is produced. If it is crossed on a way up, it's positive, and a way down, negative. This method is a bit better, as we can see here on this example. We keep the same example as before. Here is a result with divided by 5. We can kind of see the arm moving around, but it keeps a lot of noise in the background, as you can see more specifically when it is divided by 10. But it's closer to what would an actual event camera do. Another log luminance reconstruction method would be to actually reconstruct the log luminance of each pixel that is in the region that we want to downscale. So, starting from the events, we produce the log luminance. So we do the opposite of what is done actually by event camera. We start from the same 4 pixels once again, and we reconstruct the log luminance. Here we have reconstructed this log luminance using a linear estimation, so this is quicker and more computationally efficient. We compute the mean of those 4 log luminance, and then we retrieve the event produced. Here we have only 3 events that are produced for those 4 pixels, which has a more or less than the 2 previous methods. If we take a look at what it actually does using the same events as before, when it is divided by 5, we have a lot less events than with the 2 previous methods, which is one goal that we wanted to reach. However, divided by 10, we can't really understand what is going on in the picture, so it still has some cons. Finally, we kept on with our log luminance reconstruction method and tried to reconstruct the log luminance using a cubic estimation. We start by the same 4 pixels and reconstruct, thanks to the piecewise cubic Hermite interpolating polynomial algorithm, the different log luminance. This algorithm was necessary because more traditional cubic interpolating algorithms produces really high extremas and really low extremas, which produced some fictive events that we did not want to happen. We compute the mean, and then we have events that are produced. A bit more events are produced than presently with the same example. If we take a look at what it produces with the same example as before, when it is divided by 5, you can actually kind of see the arm moving around, and divided by 10, we have less noise than presently, and we can maybe kind of see something going around. The final method is the one given by simply translating events to video and then to events again. The first step would be to translate events into grayscale frames using the events to video library created by Rebecca in 2019, then rescale the actual grayscale frames by a certain factor using any of the mini tools that exist in order to do this, and then translate back those grayscale frames into events using the video to events library produced by Gerrick in 2020. This method has 2 huge cons that are, first of all, in an embedded system, this needs 3 different computational steps and processes. which will take a lot of time and not the most ideal in order to be run on a UAV, for example. Secondly, creating grayscale frames loses all the asynchronicity of an event data. Here are some variables that we computed in order to compare those different methods. First of all, we took a look at the number of events that we get. Each sample of the original full-scale DVS 138 gesture dataset is around 6 seconds long and contains an average of 194,000 events base sample. For the different methods that we implemented in this paper, when we divide the original dataset by 4, we get the following number of events. The event funneling, whether with our method or Tonics downscale method, keeps the same number of events. There is not a lot of events that are dropped, and which is a huge downfall of this method. However, using event counts, the number of events decreases to 7,000 average base sample, and with linear and cubic estimation to 600 and 400 number of events. This is more what we would like you to do. We also computed the event density, which is the mean number of each pixel activation. The event density for the round 12 for the original full-scale dataset, it increases to 180 and 89 for the event funneling methods, but decreases to 7 for the event count methods and less than 0 for the linear and cubic estimation of log luminance. This event density is coherent with what we've seen before, meaning that the event funneling methods increases the number of pixel activation compared to the ratio of the image. The event count keeps the same but with a lot of noise, and the linear and cubic estimation decreases. Is that a good thing that it decreases that much? We don't really know, and we want to be sure that the information that is kept is relevant. In order to do so, we computed the information entropy using Shannon's information theory, meaning that for each pixel and each polarity, so positive and negative, we computed the probability of activation and non-activation of this pixel and computed the following variable h plus with this equation in order to obtain this information. The original full-scale dataset has an entropy of around 10 power minus 6, which is really low, because event data by definition is really sparse. For the event funneling, we have an entropy of 10 power minus 5, and event count and linear and cubic estimation entropy of 10 minus 6 and minus 7, which are kind of stable, so we should have the same number of relevant information. Finally, we can take a quick look at the computation time, which is the time that it has taken to run the different methods to downscale 100,000 events on a CPU. The simple event funneling and tonic downscale, as I said earlier, is obviously the quickest in order of milliseconds, whereas the event counts and linear estimation and cubic estimation takes a lot more time, around 3 seconds. However, as I said earlier, one sample of the original DVS gesture dataset is around 200,000 events long and lasts around 6 seconds. So if we downscale 200,000 events, it will take around 6 seconds to downscale it using the cubic and linear estimation. So this proves that it's still possible to downscale even using those different methods in real time as soon as the events are recorded. Finally, the final component is about optical consistency. This is more of an arbitrary estimation of how much this method is akin to the mechanisms of an event camera itself, and this has been evaluated thanks to the expertise of Teresa and Bernabé, which are, as I said, researchers in microelectronics. The event funneling does not look at all at what would an event camera do. The event count is a bit more closer to it, but it still has a main downfall that it waits for each event to come in order to produce reduced events, which is not exactly what would happen on a real event camera. And the linear and cubic estimation are a bit closer too, with the cubic estimation being the closest, thanks to a cubic interpolation of the log luminance. Following this paper, we have some future work that we could develop, such as evaluating the accuracy loss in a classical computer vision task, such as classification, brought by the proposed method in order to compare them and see which one keeps the most relevant information. We could also develop event reduction using sparking neural networks, or evaluate the real-time capability of the proposed methods. also taking into account the energy consumption of each of those methods. We could also implement a variation mechanism such as the one described in our paper in 2021. And finally, we could extend our spatial downscaling methods to temporal downscaling. Here are our bibliographical references used during this talk. Thanks a lot for your attention, and thank you for assisting to this talk.